one more video. We're not going to call it review video 6 though. We're going to call it bonus round video. So all I'm doing here is I've got a bunch of multiple choice questions, read them, try to answer them, and then I'm going to cover them. And then that's it, and I'll see you guys tomorrow. Quick review on data changing. If I have a normal curve and I rigidly shift, right, so I add 100 to all or take 100 away from all of those values, then that doesn't change standard deviation at all. It just changes where the mean is going to happen, and it changes, well, that's basically it, right? So standard deviation is not affected by this rigid shifting because it's not making the curve any wider, any skinnier, like a parabola. When I just add or subtract a parabola and it moves around, same thing happens with the normal curve. So when I'm talking about standard deviation, though, that'd be like how wide the parabola is, and it's the multiplier that affects that. It's not the add or subtract. Okay, so we think about like this. We have an expected value, and we have a standard deviation, and we have a function changing our values, our x values, to profit. And so we want to think about the fact that standard deviation is not affected by rigid shifts. And so if I want to find a new standard deviation, I'm going to plug it in, but I've got to drop the minus 100 off because that's a rigid shift. If it had asked me to do mean, that would be different, and I would do both things. But because it's talking about standard deviation, I don't do the rigid shifting. I only do the multiplier. And I end up with 432, which is B. I'm going to write and talk on this one because I think it needs it. So it says you have a sample of 42 rabbits and you've got a mean weight of 5 pounds. So imagine you've got a mean weight of 5 pounds and your standard deviation is 3 pounds, right? So that's fine, that makes sense. So one standard deviation would be 8 pounds and 2 standard deviations would be 3 more pounds, which would be 11 pounds. And then maybe I might have a few really fat bunnies, so maybe I could go one more and say 14 pounds, right? Oh, you can't see that, hi. Well, the problem is that if I go this direction, right, I go one standard deviation to the left, that's fine. I have tiny baby bunnies at 2 pounds. But if I try to go another standard deviation this way, I now have bunnies that weigh negative 1 pound. So that doesn't make sense, right? We probably don't have any bunnies that are less than this. But we know the most amount of bunnies are going to be here. And then, we're going to have something like this. But then all of a sudden I can't do anything else here, but I'm definitely going to have bunnies that weigh, some weigh this much and some weigh this much and some weigh this much. So imagine what this data is going to look like, right? So this data is going to look like this, which would be skewed to the right. So our answer in this case would be C. Whoop, skewed right? But you need a little bit of visual there to see that that actually happens. For this one, it says when using a one sample T procedure to construct a confidence interval for the mean of a finite population, a condition is that the population size must be at least 10 times the sample size. So that 10% condition, that's the condition we've always used, right? Where I say, okay, there must be at least this many. It's reasonable to assume that there are that many. But actually, that rule is called the rule for independence. So if they're not independent, then you check conditions for 10%. Although the 10% condition always works. So you just need to know in this case that we replace the independent condition with 10%. So it's kind of easy. Then you can sort of see here, it says, there it is, D, the degree of dependence among observations is negligible. For this one either, because you should know that when we look at residuals, what we're looking for is, or for no pattern, for the data to be completely scattered, and so your answer on that one should have been C. confidence intervals all the time. A random sample of 50 students at a large high school resulted in a 95% confidence interval for the mean number of hours of sleep per day. And you end up, they give you this confidence interval of 6.73 to 7.67. And they want to know which one of these things is true. So now we need to understand what a confidence interval means, right? So a confidence interval means that if I were to take all the possible samples from this particular population, every single one of them, and construct confidence intervals at 95% for every single one of these, 95% of the time, the true mean is going to occur in that confidence interval, right? So if I could make a graph of all these confidence intervals, not every single one of them will actually capture that true mean, but it will happen 95% of the time. Okay, so the answer here is B, because you need to talk about capturing that true mean when you describe or explain the confidence interval. Okay. Okay, I think there's about 1 million confidence interval questions on the test. So you've got a survey in 2009 where 79% of adults are on the internet, right? And they are constructing a 98% confidence interval, and they're wanting a margin of error to be no more than 2.5 percentage points. And then it's just basically like, which one of these would give us that value, right? How many I need, or how big my sample needs to be to make that happen. And so I'm thinking, okay, what confidence interval do I need then? I need the one for proportions because it says 79%. So right there you can see, okay, I've got a P of 0.79, okay? And it tells us 98%, which is going to give us a Z-star of 2.33. And again, you don't need to do this. You don't need to look this up because it's multiple choice. So you can go straight to that concept of 98% is going to fall between 95 and 99, right? Which falls between 2 and 3 standard deviations. So it has to be the 2.331. It can't be the 1.961, okay? And then here is my formula right off the formula sheet for Z-star. Well, you know, it's got the P plus, but we're going to leave that part off because it's not necessary when I'm just wanting to solve for N. And I want it to be less than 2.5%. Or 0.025%. And really then it's just a matter of saying, oh, it's D. And if you got trapped into thinking maybe it was the less than 0.051, if it had a plus or minus in front of it where we're looking at the whole interval, then it would be 0.05. But because I'm just looking at the positive one, then I'm just looking at mean plus the standard error, okay? A manufacturer claims its brand A battery lasts longer than its competitive B battery. 9 batteries of each brand are tested independently, and they give you battery life in hours in the table for A and B. Okay, so the first thing that we want to do is note that there are 2 variables in the data right off the bat. Okay, so it says provided the assumption for inferences are met, meaning we can run a test on it. Which of the following tests would be conducted to determine if A batteries do in fact last longer than B batteries? Okay, so I'm going to answer this question, but then I'm actually going to run you through this test because this is the kind of test that StatsMedic suspects will be on the open response for like the question 4 or 5 where they actually do that, the full significance test, okay? So here's the question. Oh gosh, try not to erase anything because it took forever. So here's like the table, right? You know there's 2 variables. If you think about what the hypothesis would be in this case, it would be that there's no significant difference between the battery life. And so that means if I were to take the mean life of each one, they should be the same. So that would be your null hypothesis, is that there's no difference. In your alternate hypothesis then would be, because the question asks, does it actually last longer? So that would be your alternate. This is the one you're trying to prove. So that means the mean A would be bigger than the mean B. Assuming we're going to run this at a 0.5 significance test, which test would we run then? Okay, well, we've got 2 samples, brand A and brand B. It's going to be a t-test because look how small your sample sizes are, right? Your sample sizes are way too small to run a traditional z-test. And then it's going to be a one-tailed test or a one-sided test because it says greater than. So remember, greater than or less than is just one tail, but if it were not equal to, that's when you need greater than and less than, so that's your two-tailed or your two-sided test, okay? So your answer here is B. Let's say I want to run the full test though, okay? So that means I need to find the mean of A and the mean of B and subtract them. So here's the mean of A, the mean of B. Here's the mean of A minus B, which is 5.3, okay? Then I need to find the standard deviation. So I actually ran a one variable statistics in the calculator to get these values. I get a mean or a standard deviation of 5.24, standard deviation of 2.87. This formula for standard deviations on a two-sample test is on your formula sheet, okay? So you're just going to plug in and you're going to get that standard deviation is 1.99. Remember, when you're subtracting, you can't actually just subtract standard deviation. Then your degrees of freedom is 9 minus 1 or 8. Find your t value, which is mean minus what we would like the mean to be, which is 0, over standard deviation divided by the square root of the sample. We end up going to the calculator to run TCDF, and we get a p-value of 0.009. So we would, in this case, reject the null hypothesis, okay? So this would be your full test run. I didn't, of course, write the full paragraph at the end, but for how you would do the difference, okay? Easy question. An experimenter conducted a two-tailed hypothesis test on a set of data with a p-value of 0.44. If the experimenter had conducted a one-tailed test on the same set of data, which of the following is true about the possible p-values that the experimenter could have obtained? Okay, so what happens is he ran a two-tailed test, so that means his alternate hypothesis was not equal to, and the two-tailed test looked like this, right? Well, if he ran a one-tailed test, he would have only had half the area. So we take our p-value and divide it by 2. And that means we could have had a two-tailed test on this side, so it would have been 0.22. Or we could have had a one-tailed test over here, or a one-tailed could have been over here. And in that case, it would have happened at 0.78, right? Because that would be 1 minus the 0.22 to give me the tail on this end. So the answer would be D. So another question asking about whether or not, or what type of test you should be running. So you should look at this, see that it's a frequency graph, and know immediately, okay, it's frequencies, so I know I'm going to use a chi-square of some kind. So then they give you two chi-squares. One is goodness of fit, the other one is independence. Goodness of fit means you have one variable. You're wanting to know how well that one variable fits in the population, right? So the sample, how does the sample fit in the population? The other one is independence, and we used association more than we used independence because I think it makes more sense, right? So two variables means you're going to be looking for a comparison or an association between those two variables. In that case, we call that independence. Are they independent of one another, or is there some kind of association? So the answer to this one is E. Number of randomized experiments were conducted to determine whether taking a particular drug regularly would decrease the chance of getting a certain disease. So in the experiment, you have people taking a drug and people taking a placebo. And the question is, you're gonna take the difference between the two, okay? And if the drug had no effect whatsoever, then we want to know which one of these things will be true. So the first thing you need to do is determine what's the null and alternate hypothesis here, right? So our null hypothesis is we take the difference of the two, the proportion of people taking the drug and the proportion of people taking the placebo, and we want that to be 0. We want no effect to happen. We don't want that necessarily. We probably want this to happen where there is some effect. But this particular thing says that there is no effect. So we would go with that we would go with the null hypothesis. So first one says p-values will be greater than 0.05 for 95% of the experiments. So our p-value greater than the alpha level, yeah, if it had no effect, that would have occurred, right? It wouldn't have been shocking. Next one says there will be an equal number of experiments showing positive and negative values of drug effects. So that means that the p-values from the drugs and the p-values from the placebos will be the same. Yeah, that's exactly what the the null hypothesis says. And then the third one says when 95% confidence intervals for the population drug effects are constructed, those confidence intervals will include 0 95% of the time. So earlier I drew you a picture about this, but yeah, basically that's an explanation of what a confidence interval is and does include the true, in this case, the true proportion of 0. So yep, E is the answer. All three are correct. As a part of a class project, a large university, Amber selected a random sample of 12 students in her major field of study. All students in the sample were asked to report their number of hours spent studying for the final exam and their score on the final exam. A regression analysis is provided. Okay, so you've got that table of regression analysis. And so the question is, which one of these in the multiple choice section will give you the margin of error for the confidence interval at 95%. Okay, so just a quick reminder on the table. Looking at the table, your constant coefficient, that's your B for y equals mx plus b. Your study hour, the other thing under coefficient, is your m for slope. Your standard of error, so just ignore this one. This is your standard of error, 0.745. And then all the way over here, we like p-value, and then, of course, t-value. Okay, and then we have our value for residuals, our standard deviation for residuals, and then our variance. Okay, we want to remember that a confidence interval is a point of interest plus or minus a margin of error, and they're asking about the margin of error piece only. Okay, so we can find, this should say margin of error is going to be 95%, our z star, times our standard of error. And so this is given in every problem, so we don't have to worry about that. Basically, they're asking, do you know which error piece to pull? And remember, it's always for the variable one. It's never for the constant one. So when we're looking for margin of error, we use the standard error from here times our z star. Okay? Which is, I didn't write it on here. A. Okay, there were 5,317 previously owned homes sold in the Western City in 2000. The distribution of the sales prices of these homes strongly right skew to the mean of 206,274 and a standard deviation of 37,881. If all possible simple random samples of size 100 are drawn from this population and the mean is computed for each sample, which of the following describes the sampling distribution of the sample means? So what we're looking at here is, does the mean change and does the standard deviation change? So the mean does not change. In the sampling distribution, the mean will stay the same, but the standard deviation will actually get smaller. So, and Jeremy, that's what we talked about earlier today. So we have a mean that stays the same, but a standard deviation that's going to take what was the standard deviation and now divide it by the square root of the sample size, and we end up with 3788.1, which is A. So remember, mean stays the same, standard deviation smaller. Okay, guys, I'll see you tomorrow for yoga, lunch, review, and the test.